Excellent. So welcome everyone. We're very happy to have Jieqiang Wu today, who's going to tell us about algebra of diffeomorphism invariant observables in JT gravity. So Jieqiang, take it away.
Okay, first, thank you for having me. This time I will talk about algebra of diffeomorphism invariant observables in Jackiw-Teitelboim gravity. The talk is based on this work cooperated with Daniel Hallow. In this work, we revisit the Peierls bracket, which is a covariant way to compute the observables bracket by linear response picture. With Peierls bracket, we started the algebra of diffeomorphism invariant observables in Jackiw-Teitelboim gravity. The observables include pure gravitational ones and gravitational dressed matter fields. I will explain later what's the meaning of pure gravitational observables and gravitational dressed matter fields. And with the algebra between pure gravitational observables, we can easily reproduce some old results in Jackiw-Teitelboim gravity, including SL2 charges, traversable wormhole, and the scrambling effect. And with the brackets generated by the gravitational dressed observables, we revisit the Markov-Paczynski's firewall argument. In the talk, I will first give a brief introduction for diffeomorphism invariant observables, and then I will introduce the formalism of Peierls bracket. With the Peierls bracket, I will study some observables in Jackiw-Teitelboim gravity. And then with this bracket, I will give two applications. First, reproduce some old results in Jackiw-Teitelboim gravity. And finally, we will go back to the firewall argument. The diffeomorphism symmetry is a technical difficulty in gravitational theory, but it appears almost everywhere. And as we all know that the diffeomorphism symmetries should be treated as gauge symmetries. And for theories with gauge symmetries, only gauge invariant observables are physically intrinsic. And in this work, we will only focus on classical limits. So for most of the time, we will refer the operators as observables. QED is a well understood example for theory with gauge symmetries. And in this picture, we focus on these two operators. The Wilson line attached on two matter fields, like this one, and a Wilson line attached on a charged matter fields and the spatial boundary, like this one. And from these two examples, we see that for gauge invariant observables, the charged matter fields are always associated with the gauge fields. In another way to say is that if we create a charged particle, it should always be associated with the gauge fields to satisfy the constraint equations. In gravitational theory, it is similar. The matter fields should always associated with gravitational fields, which is usually referred as gravitational dressing. And the standard treatment for gravitational dressing is relational construction. That means instead of locating the matter fields in a special point in a coordinate, we can locate it in a covariant way. For example, here I gave one example for the gravitational dressing. We can shoot a geodesic from the spatial boundary with given distance, like in this picture. And we measure the matter fields at the endpoint of this geodesic. Here, this 1s0, it is a functional of the metric, which can be interpreted as a gravitational Wilson line. And the goal of this work is to study the physics effect of the gravitational dressed observables and other diffeomorphism invariant observables. And for this problem, the first question may be to study their brackets. Before going into the details, let me give two motivations to study the diffeomorphism invariant observables. The first motivation comes from the gravitational evolution. So let's see these three pictures. This is eternal wormhole. And in eternal wormhole background, to study the black hole interior, naively, we may try to involve the boundary time. Like in this picture, And you see that the green Cauchy surface indeed touches the interior of the black hole. But we may also try to involve it in this picture, like this red Cauchy surface. And you see that the red Cauchy surface do not touch the interior of the black hole. And the evolution between the red Cauchy surface to the green Cauchy surface is actually generated by the constraint equations, which is actually trivial in physical phase space. But on the other hand, we know that the observables inside and outside the event horizon are indeed different ones. So we need a diffeomorphism invariant way to describe the observables behind the event horizon. The second motivation is related to the firewall argument. Here, I will refer the Maro-Paczynski's firewall argument. Assuming that the effective field theory still works close to the event horizon, then we can try to consider the following process: creating a particle behind the event horizon, and the ADM energy will decrease. However, this result is contradictory to the lower bound of the spectrum, so it implies that close to the event horizon, the effective field theory does not work. However, this argument based on the Keeling symmetries of the Schwarzschild metric, and it also takes an approximation where they treat the system as a field theory on curved spacetime. There may be two weaknesses or two directions to strengthen or modify this argument. The first is about typicality. So the firewall argument is for typical state. So we do not expect that the black hole should have Keeling symmetry. The macroscopic state of the black hole should have Keeling symmetry in its interior. And we should consider some more general configurations than the Schwarzschild metric. The second is about the gravitational dynamics. Since here we are discussing the black hole physics, so the metric should be treated as a dynamical field instead of a fixed background. So we should include the gravitational dressing for the matter field's creation. So far is the introduction. So any question? Okay. Then
can I ask a question? So is it clear how to do the gravitational dressing in the presence of horizons?
I mean, usually the way it's not clear to me how to find all of the gravitational dressing, but I have some way to do the dressing. Usually I will give a diffeomorphism invariant way starting from a reference point, but the reference point is always from the spatial boundary.
Right, and you can cross the horizon the way that you do. Okay.
Yes, I can.
Okay. Thanks.
Yeah, well, so about this Peierls bracket, before I introduce the Peierls bracket, let me first briefly review the Poisson bracket in canonical formalism, which is well known in classical mechanics. We start from the theory with this action, and we define the conjugate momentum like this. And the phase space is labeled by the coordinates and the conjugate momentum. And we introduce Poisson bracket like this for any two functions on phase space which are observables. And their Poisson bracket can be computed in this way. And in principle, we can also define observables as functionals of the configuration like this. But for these observables, to compute their brackets, we first need to choose a Cauchy surface, and we solve the solution by their initial values, and rewrite these observables as function of the initial values, and then go back to previous step to compute the Poisson bracket. So you see that even for this kind of observables, the computation is already complicated. And actually, for the Poisson for this canonical formalism, there are more drawbacks. First, there is no explicit covariance for field theory, and since we need to choose a time direction. Second, for series with higher derivatives, it will be more complicated. And third, for theories with gauge symmetries, we need to introduce gauge fixing and also play with the Dirac bracket. That will be very troublesome. but Peierls bracket solves all of these drawbacks. The Peierls bracket is a covariant computation for bracket with linear response picture. We may get some inspiration from this quantum mechanics problem. We consider two states, the initial state omega and another state, an involved state. Here, this lambda, I assume it is a small parameter. And we use an operator O to measure their difference. So we measure the difference of their expectation value. And to the linear order with respect to lambda, you see that it is proportional to the operator commutator's expectation value. And on the other hand, we can also use the linear response picture to describe the operator's commutator. And indeed, it is true, at least in classical mechanics, the brackets between two observables can be interpreted as the linear response of quantity f to the deformation of the action by minus g. And I will explain the detail in this page. Here f and g are, here I assume f and g are two observables, and their Peierls bracket is defined in this way. Here this phi is a solution, and third phi is a linearized solution about phi. And this third phi depends on g and is determined in the following way. We consider a deformed action in this way and focus on these two classes of solutions, the retarded solution and the advanced solution, such that this third phi vanish at past infinity for the retarded solution, and this third phi vanish at future infinity for the advanced solution. Neither the retarded solution nor the advanced solution satisfy the original equation motion, but their relative difference gives a solution for the linearized equation. Or another way to say is that this third phi is a vector in the set of solutions. This gives us the definition for the Peierls bracket. Any question about this definition? Okay, anyway, I will show more examples to illustrate this definition. And for theories with gauge symmetries, this third phi may have ambiguities, but their bracket is unique if both f and g are gauge invariant observables. And another comment about this formalism is that from this definition, you see that it is not apparent that the bracket between f and g is antisymmetric. And this is both a good thing and a bad thing. The bad thing is that it is not apparently antisymmetric, and the good effect is that we can use the antisymmetry as a cross-check for the computations. And in our work, we compute for each of the bracket, we compute it in two ways. We choose one of them as a source term and the other observables as the measurements. Maybe this definition is too formal, so let me illustrate it with these four pictures. The first picture is the original solution, and then we introduce a deformation. We get this evolved solution. We get this retarded solution. Sorry, an advanced solution. With a proper combination of these two, we get this evolved solution. And both this original solution and this evolved solution satisfy the equation motion. And for any other observables, we can measure the relative difference between this solution and this solution. It gives us the bracket. And furthermore, most of the time, the observables that we are interested in, it only support at one Cauchy surface. And for this kind of observables, we can start from this retarded solution. And starting from the past and evolve forward, we get the original solution, or starting from the future and evolve backward, we get the evolved solution. And the relative difference between the evolved solution and the original solution are captured by the relative difference of the initial values between the upper side and lower side of the Cauchy surface. And another comment is about the covariant phase space. The covariant phase space is another covariant Hamiltonian formalism And covariant phase space, and actually covariant phase space is the most natural formalism to introduce Peierls bracket. And one can prove the Peierls bracket is equivalent to Poisson bracket defined on covariant phase space. And with this equivalence, we can easily show the antisymmetry and Jacobian identity. However, in this talk, we will not mention anything related to the covariant phase space, but only to illustrate the Peierls bracket by some concrete computations. And let me try to illustrate the Peierls bracket with a simple example, the point particle, with this action. And we try to use Peierls bracket to compute the brackets with this observable. Here, x0 and x0 dot denote the zero-time coordinate and conjugate momentum. And as I mentioned, I need to solve the retarded solution and advanced solution, and also their proper combination, this evolved solution. And we directly couple this observable into the action. Then we have this deformed action. From variational principle, we get this equation of motion. You see, we have this source term, and from it we can get the solution like this. And you see that in this solution, the behavior for t smaller than 0 and t bigger than 0 are different. And for any other observables, for example, x0, we can measure the bracket. We can measure the difference of the observable between the lower side. For any other observables, we can measure its relative difference between the lower side and upper side of this t equals to 0 surface. For example, from this term, we can read out the brackets between x0 with this observable. And from this, we can read out the brackets between the momentum with this observable like this. And for any other observable, which is a function of the coordinate and conjugate momentum, the brackets with the observable g is like this. You see that the result is consistent with the Poisson bracket. And furthermore, from this computation, you see that the bracket is captured by the discontinuity at t equals to 0, which will also be true in the following examples. So any question about this example? Okay. So far it is the Peierls bracket formalism, and in the following I will use the Peierls bracket to study observables in Jackiw-Teitelboim gravity. So here we need to first introduce some diffeomorphism invariant observables and then study their effect. The first two well-known diffeomorphism invariant observables are the ADM energy in the left-hand side and right-hand side. And to describe other observables, we need to introduce two classes of geodesics: the geodesic connecting the two spatial boundaries and the geodesic shooting from the left boundary. Here, t minus and t plus denotes the boundary time where the geodesic end up at the spatial boundary. And this eta, it denotes a relative boost. It actually denotes the direction to shoot this geodesic. On the geodesic and on the spatial boundary, we can define a local frame, and this eta denotes the relative boost between the frame on the geodesic and the frame on the spatial boundary. And with this two-sided geodesic, we can define several other diffeomorphism invariant observables. For example, the geodesic distance, and also the relative boost between this geodesic with the two spatial boundary. And furthermore, with the geodesic, we can also locate a point on the geodesic and measure the matter fields. It gives us the gravitational dressed matter fields like this. And indeed, when we take the cutoff to infinity, several fields with several quantities, several observables will goes to 0 or goes to infinity. So we need proper renormalization for some of them. These are all of the observables that we will study. And in the following, let me show one example to use the Peierls bracket to study the brackets. And here I will choose the simplest example, that is the geodesic distance. and I will start in some brackets with the some brackets with the geodesic distance. As I mentioned, this is the original action for the JT gravity coupled with the matter field. As I mentioned, to start a bracket with the geodesic distance observable, I need to couple it to the action, and then we have this deformed action. And we need to use variational principle to study the deformed equation motion. So here we need to take a variation for the geodesic distance, as in this equation. Actually, it has two contributions for the variation. First, it comes from the variation from the metric, and the second comes from the variation of the curve. But since the geodesic already take extremal values, so the second contribution will vanish. And the variation of the geodesic, it is a one-dimensional integral for the variation of the metric along the geodesic. And from variational principle, we get this equation, we get this deformed equation motion. And to solve it, we focus on a special component, that is to contract with the parallel component. And then we get a second order differential equation. You see that there is a third term here. And we focus on the geodesic, and we can easily read out the discontinuity of the Davidson field like this. So from this result, you see that the Davidson field itself is still continuous, but its time derivative is no longer continuous. And with the boundary condition, we can read out the relative difference of the boost between the upper side and lower side of the Cauchy surface. This can be read out in this way. So from this result, you see that between the upper side and lower side on the geodesic, the Davidson field is continuous. So their tangent direction derivative are still the same. But from this, we know that their normal direction derivative have a jump. But from the boundary condition, we know that along the tangent direction of the spatial boundary, the derivative of the Davidson field should vanish. So the boost between the frame, the UN frame, and this tau E frame should have a jump. Then it gives us this result. And from this, we can read out the brackets between the boost and the geodesic distance observable. And the renormalization, we have this result. Actually, from this result, we can easily read out the well-known traversable wormhole effect. In these two, the traversable wormhole effect was discussed in these two papers, where they consider some coupling some coupling for the matter fields between the two spatial boundaries. And after we integrate out the matter fields, it will reduce to some function of the geodesic distance. And it is this geodesic distance which decrease the boost, which means that the two spatial boundaries are bent towards each other. So it opens a small window such that an early time ingoing particle can go across this small window. So any question about this computation?
Yes, I have a question similar to the previous one. So in that case of Gauss wall, you know that you have a two-sided black hole, right? Originally with a non-traversable wormhole, but then they make it traversable. In your case, as far as I understand, you can have, for example, pure ADS, right? So there is really no black hole. So in some sense, already everything, the two boundaries are communicated, right? How can you be sure that there is a black hole in there? Did you change the geometry in the bulk, or?
I still need to turn on some deformation, turn on some non-local deformation. Say like, right. We need to introduce a deformation which is related to the geodesic distance.
Okay, I will wait. Thanks.
Is it clear?
Not completely, but thanks. Okay, I will think about it.
I think Jieqiang is talking about he's just picking a background on top of which he defines diffeomorphisms in invariant observables.
Agree.
His contribution is to show us how to compute brackets with his observables in some useful way. So I think the background is an input, I think, in his discussion.
Right.
Yeah, so maybe
But-
can I?
But okay, so you are claiming that you can do this regardless of whether the background is a black hole or is just pure ADS, right? So it's independent of that.
Well,
This
so I
construct-
need to.
suppose it is, right? Somehow.
Sorry, say that again.
Is it independent, this construction of the background, or? I mean, you can do it for any background, or if there are horizons, one should be more careful. That's the
Well, but
question,
I think
essentially.
I mean, indeed, for this observable, since this is in Jackiw-Teitelboim gravity, so the background should always be the system with two spatial boundaries.
Right, but it's different to have just pure ADS too. This has two boundaries, right?
Yes.
And to have a black hole, a two-sided black hole, right, with
Yeah.
horizons that essentially, with no violation of the null energy condition, you cannot cross, right? So it's different physically.
So I didn't quite understand your comment.
No, well, I'm just asking whether your formalism can be applied in any case, in any, or
I
it's
mean,
something that can be done, just for
Yeah.
when there are no like eternal black holes, or if there are
I mean-
restrictions, or that's the question.
I see. I mean, in principle, this formalism can be used for any background, but here to use this formalism, understand the traversable wormhole effect, I choose a special background that is this eternal wormhole background.
Okay.
Yeah, but in the in the very end, you will see that we can also study some other observables in some other background, which is not the pure ADS, which includes some matter fields, and it also works.
Okay, thanks.
Maybe I can, let me first go ahead. And so as a cross check, we try to reproduce some of the old results in Jackiw-Teitelboim gravity with the algebra that we get. Here we focus on the observables generated by these observables, the ADM energy, the boost, and the geodesic distance. And we first try to reproduce the SL2 charges, which was developed in this paper. And from these observables, we can define three other observables, which is P0, P plus, and P minus. And with the algebra that we get, we can easily check that this P0, P plus, P minus, they have their algebra is like this. And you see that from the first line, you can see that they build an SL2 algebra. And from the second line, you see that the matter fields is a representation for the SL2 algebra. And from the third line, you see that the geodesic distance commute with the observables that we define. So you see that, so from this we get some results like this P lambda vanishes in pure Jackiw-Teitelboim gravity, and furthermore it builds an SL2 algebra which acts on matter fields but not on metric. This is a result that is derived in this paper, and we reproduce their results. And the second cross check is about the scrambling effect. Here we try to reproduce the results in this paper. And in this paper, they consider such a process, like shooting a light particle at a very early time and measure the geodesic distance at t equals to 0 time. And they found that at t equals to 0, the geodesic distance to the leading order perturbation, the geodesic distance has an exponential increase behavior. And to use our formalism, we take a relative boost. We insert a particle at t equals to 0 and measure the distance between this point and this point. And second, we use a Hessenberg picture. Then we try to rewrite this operator as some operator. This operator at t minus and t plus by some operator at t equals to 0. Here from this, we can get a differential equation by taking a derivative with respect to the left and the right time. We can this derivative is can be described by the brackets between these observables, which can be computed, And by solving this differential equation, we get such a result where we can rewrite the geodesic distance with different left and right time as some observables at t equals to 0. You see that we can rewrite it by the 0 time geodesic distance, the relative boost, and also the ADM energy. And from the inside of the bracket, you see that we have this cosine and sine function. And to the leading order deformation, it is this cosine function and sine function that gives us the exponential behavior. And to the leading order perturbation, we get such a result. You see that we reproduce the exponential increase behavior, which is the result from this paper. So far is the cross-check for the Peierls bracket, where we use the Peierls bracket to reproduce several previous results. And any question? Okay, so finally we will go back to the firewall argument. And to start is the firewall argument, we first need to discuss the gravitational dressed matter fields. Here we consider a special gravitational dressing by shooting a geodesic from the spatial boundary and measure the matter field at this point, at the endpoint. And you remember that in Peierls bracket, we need to compute the variation of this observable. Here, this y mu s, this curve y mu s, this geodesic y mu s, it is a functional of the metric, which satisfies the geodesic equation. And taking a variation with respect to the metric, we get this second order differential equation for third y mu. And this third y mu can be solved in this way. Here we take a decomposition along the tangent direction and normal direction. And both alpha and beta are integral of the variation of the metric along the geodesic. And the variation of this gravitational dressed observable is like this. Here, this alpha and beta are written here. And as previous discussion, we will use the Peierls bracket to study the brackets with this gravitational dressed matter field. And we directly couple it into the action and consider this deformed theory. And by variational principle, we can get the equation motion, and then we can solve the discontinuity of the Dyson field and its time derivative like this. So you see that different from the previous example. In this case, the Dyson field itself is also discontinuous across the geodesic. And there are some subtleties about the boundary jump, but here I will not discuss it. And from these discontinuities, we can easily read out the change of any other observables. For example, we can read out the change of the ADM energy, and then we get this result, which will from which we can read out the brackets between the ADM energy and the gravitational dressed observable. And in principle, we can consider some other operators with this gravitational dressing. For example, this is an operator that we already have, and we can also consider its time derivative, its time derivative. And with these two operators and smearing with proper weight packet, we can define such a creation operator, which create a local packet with the center of location at this point and the center of momentum. And we can compute the commutator between this ADM energy operator with this gravitational dressed operator. In semi-classical limit, we will use their Poisson bracket to do approximation. And here I take a shortcut. I directly take the time direction derivative to the IK, and then we can read out such a behavior. You see that the coefficient here gives us the energy change of the system. Here I will just refer them as excitation energy. And you can see that for small geodesic distance, this excitation energy is positive, and for long geodesic distance, this excitation energy is negative. And if we choose eternal wormhole background, this excitation energy changes signature at the event horizon. And you may wonder that this excitation energy is independent of whether the particle is ingoing and outgoing. That is because here, for simplicity, I choose it equals to 0, where the geodesic is shooting orthogonal from the spatial boundary. If we choose a general it for this creation operator, then the statement is only true for the outgoing excitation. For example, in these 3 pictures, where a blue arrow denotes an excitation with positive excitation energy, and a red arrow denotes an excitation with negative excitation energy. Say, for example, in the middle picture, here, an outgoing excitation will give us a negative excitation energy, but an ingoing excitation will give us a positive excitation energy. And we also consider more general backgrounds, which is for the multi-shockwave solution. And we found that the statement is still works. That means the excitation energy changes signature at the event horizon. But I think this may come from the special effect of the Jackiw-Teitelboim gravity and the multi-shockwave solution. The reason is the following: in global coordinates, the solution in JT gravity, the JT gravity solution can be written in this way. And we found that this A, B, C, these parameters, they are all the same for all wedges attached to the spatial boundary. For example, in this picture, in all of these gray regions, the solution are the same. So starting from any one of these wedges with the ADM energy, we can easily figure out the location of the event horizon. And then let me give the final statement. So when we create an extra outgoing particle in front of or behind the event horizon on multi-shockwave configurations by the state-independent gravitational dressing operator, the ADM energy will increase or decrease. Here, by state-independent, I mean for any state. In principle, when we talk about an operator, it is always state-independent. Here, by state-independent, I mean that for any state with a given energy, we can use the same operator to create an extra particle in front of the event horizon and increase the energy, or behind the event horizon and decrease its total energy. And our statement, we checked several examples and we found that our statement is still true for higher dimensional case up to a small fraction. So in this sense, we more or less strengthened Marov and Pertinsky's firewall argument. But going back to the Marov-Pertinsky's firewall argument, it's still far from making any concrete statement. For example, about typicality, indeed we consider some more general states, but it's not clear to me whether the multi-shockwave states are really typical state or not. Maybe there are some other more typical states. And indeed, we consider one gravitational dressing, but maybe that is not the most reasonable gravitational dressing. Maybe there are some other choice. And in our discussion, we only consider the semi-classical effect, and we haven't included any quantum corrections. So these are the loopholes of the argument. So that's the reason I said it's far from making any concrete statement about Marov-Pertinsky's firewall argument. Let me give a brief conclusion. In this work, we do concrete Peierls bracket computations in Jackiw-Teitelboim gravity. We reproduce some old results in Jackiw-Teitelboim gravity, which were studied by Schrödinger formalism, and we revisit the Marov-Pertinsky firewall argument. Thanks for your attention.
Very nice talk, Jieqiang. Do you have any questions?
Yeah, maybe I'll just ask. So I'm curious whether you have in mind any other applications of this Peierls bracket technology. Since are there other gravitational calculations that people have had difficulties with using other formalisms that this could help with?
I don't know. I mean, the reason is I mean, usually I feel like any gravitational computation, especially in Hamiltonian formalism, will be very hard.
Yeah.
So currently there, I don't have any concrete thing in my mind that whether I have some some other application for this formalism. But you know that in principle in gravitational theory, if we want to do canonical formalism, we always need to play with this gauge fixing and direct bracket, which will, and the direct bracket, in direct bracket we need to take an inverse for an infinite dimensional matrix. That will be very troublesome, and I feel like this Peierls bracket, at least it will simplify something, but I don't have concrete examples.
So, Jason?
Yes.
Can you hear us? Because our connection is a little unstable here, so we're missing parts of your comments. So in summary, is the fair summary to say that there is a puzzle when you try to quantize fields on top of a black hole background, and the puzzle comes from the fact that semi-classical QFT would tell you that there exist observables, naive observables that you can act and excite in the interior of the black hole and reduce the energy of the black hole. And one worry that you may have is that perhaps if you try to make these observables diffeomorphism invariant, then this weird effect of introducing a particle in the interior that reduces the energy will go away. So your computation shows that at least in this setup, or using your formalism, you can do the precise brackets associated to these diffeomorphism invariant observables, and the problem persists. Is this a fair kind of summary of the main point of in the black hole setup?
Yes.
Okay, thanks. Yeah.
Yeah, so naively we may expect that after including this gravitational dressing effect, or maybe considering some more general typical state, something will be modified, but finally it is still the same as a naive analysis.
And your calculation was to leading order in H bar, is that right?
Yes.
The semi-classical. Is there any hope of exactly quantizing this theory, even with the extra matter fields, like Jafferis and Harlow did for pure JT gravity?
I'm not sure, but I think even in Jeffrey Hollow's work, they claim that they, in my interpretation, they only get a classical result, but because this system can be fully solved, so they can have more control for the system and they can quantize it as the way they want.
Mm-hmm.
But especially for an infinite dimensional system, I don't know. I mean, for a system with infinite degree freedom, I'm not sure. One can still try to quantize it, but maybe the quantization will lead to some problem. I don't know. At least from so far, I don't know how to quantize the system.
Mm-hmm. I see.
Any more questions? Okay, let's thank Jieqiang one more time.
Okay, thank you for having me.
And let's stop the recording.